Today I will be showing practical uses for hardware-assisted memory visualization. Before I start, I have to point out that I'm giving this talk as an individual. My employer is not involved in any way. I'm here today to show you the memory process file system, which is a different way of visualizing in-memory Windows internals and objects as files and folders in a file system. We'll also have a look at two different use cases. First, how I used an early version of it to find the Total Meltdown vulnerability, and then how other people have been using modified versions of my software in order to do hardware-assisted cheating in games. After that, we'll go more in depth. We'll have a look at its capabilities, its design, the API, and plugin functionality. Throughout the presentation, I will do demos, lots of demos, live demos, so let's hope everything is working. My name is Ulf Frisk. I'm working as a pen tester by day in the financial sector in Stockholm, Sweden, and I also try to do some security research by night. I'm the author of the PCILeech Direct Memory Access Attack Toolkit, which I presented 2.5 years ago at DEF CON. At that point in time, most people thought DMA attacks were a thing of the past, since CPU vendors had introduced their IOMMUs into their CPU designs a couple of years earlier on. That was quite not the case. I found a really low-cost, high-performant piece of hardware that was able to do DMA straight into memory below 4 gigs over PCI Express. At that point in time, that was plenty to attack most major operating systems. The hardware, it got kind of popular, it sold out, and also the 4 gig limit was very boring, so that's why I introduced last year at the CCC, or a little bit over a year ago, public FPGA-based DMA attacking, and now we're able to access the whole memory space of the target system. Everything that I've been doing as 100% open source, and up until now it's been very attack-focused, but I thought it would be kind of awesome to do something for the blue team as well, and that is what the memory process file system is. It's a memory analysis tool with a very strong Windows focus, which allows you to visualize in-memory objects as files and folders in a file system. It comes with a C and Python API, and if I combined multi-threading together with a native C core and some intelligent parsing in there, it's quite fast. It also comes with a wide range of memory acquisition methods, both hardware-based ones and software-based ones. So let's do our first demo for today. Let's mount a memory crash dump file, which I created with Matt Swish awesome dump it tool, and let's do some point-and-click analysis. This memory dump, it's kind of big. It's almost 32 gigs here, so let's mount it. It's already mounted. Let's have a look at it. We can click into it's mounted as the M drive. If we click into the folder, we see in the root folder, we see a copy of the entire physical memory. This is not really interesting since we are mounting a physical memory crash dump file, but imagine if you're running with the FPGA system, that is going to be super nice to have this file in order to do memory dumps. We have a status directory which contains various configuration files and configurations options and some statistics as well about the internals. But more interestingly, we do have a folder which contains all the processes on the running system. The information is gained by parsing the actual physical memory of the physical memory dump or live memory if we're using the FPGA. We can click into a process, and in the root folder of a process, we do have some files and also some directories. For example, we have the base of the page tables itself, the directory table base, or the PML4 if we are running in 64-bit mode, the address of it available as files. And since it's available as files, you can use your own favorite tool parsing this and script against it or do whatever. We can have a look at the memory map as well. The memory map is created by walking the actual page tables that the CPU uses to translate virtual addresses into physical addresses. We also try to find out which permissions bits these have, if it's a read-write, read-only, or read-execute, for example. And we also try to auto-identify which kind of memory this is, if it belongs to some modules, for example. We also have a virtual memory file, and this is a copy of, it's huge here, as you can see. This is a copy of the entire virtual memory space that is available to use in mode. You can open it in your favorite hex editing tools, for example, have a look at it, have a look at the memory in there, or if you're using a write-capable device, such as the FPGA device I will be showing in a short while, you can even do writes to this memory. We have some subfolders as well. We have a Python subfolder, and everything under here is generated by tiny Python plugins that you can create yourself. For example, we are generating on the fly when we are clicking into the folder a file that contains the actual e-process structure in the Windows kernel of the process that we are clicking into, explorer.exe in this case. We have a module subdirectory, which contains all loaded modules as in the process as files and folders. For example, you can click into 7-zip, have a look at its exported functions. We can have a look at its imported functions. And by just clicking on files, and here we see where the memory address of the function is, the name of the function, and also which module it's loaded from. We can have a look at things like sections, and it's available, and we see the addresses and the permissions. And we can, if we do wish to have a look at the sections in our hex editor, we can even open it in our favorite tools like that. And if we are running against a write-capable device, we are even able to write to these sections as well. So, but the writing is much easier if we are using the FPGA board. And we can do live analysis with a hardware device as well. And I do have my analysis computer here today. It's my presenting computer. And I do create in software the PCI Express transaction layer packets, a memory read packet in this case, wrap it in some extra metadata, which allows me to transmit it over USB 3 onto the FPGA board. Once it reaches the FPGA takes the raw PCI Express transaction layer packet, puts it on the PCI Express of the target system. Today, I'm using Express card here for convenience, but you may also use other things like Thunderbolt, for example. Once the PCI Express transaction layer packet reaches the target system root complex, it reads the memory of the target system and responds with a complete tune packet containing the actual data read. Transmits it back to the FPGA, which then forwards it back to the analysis computer. This way, we are able to both read and write physical memory with a hardware device. So let's do another demo. Let's have a look at that we can acquire some live memory with this hardware device. And we also see how changes on the target is auto-detected. So I already, if you switch to the FPGA, yeah, we have it on the screen. Awesome. And I'm already mounted it. And we are running some background refreshes here in the background that allows us to detect new processes running. This is the view of this system here, and this processes. And as you can see in the process list, if we scroll down to M here somewhere, we don't have the paint process started, for example. So we can start the paint process, and it started. And let's see if we can do a refresh here, if it appears. If it appears, yes. And it appears here. So we are doing background process refreshes, and everything that is changed on the system is auto-reflected in this file system. This pmem file that we talked about earlier on, the physical memory file, we can dump the physical memory of the target system by just copying the file in Windows Explorer. And now we're dumping the physical memory of this computer here at speeds around 40-50 megabytes per second. So let's continue. I will show the first use case. It was me when I was creating this really early version, how I came across a Windows 7 Total Meltdown. It was a local privilege escalation vulnerability that allowed any user to escalate the kernel trivially. It allowed arbitrary physical memory access and allowed memory reads and writes at gigabytes per second. It only affected Windows 7 and 2008 R2, and it was something that was introduced last year in January in the Meltdown patches. And it looked like it was patched in March last year. But I didn't see anything about it in the release notes from MSRC, and I thought the issue was really interesting, so I wanted to write a blog entry about it. So I contacted MSRC, and they got back to me a couple of days later on with an OK to publish this blog entry. And in order to make it a little bit more interesting, since it was fixed, right, I decided to publish a proof of concept as well, as you should do. Only problem was, it wasn't fixed, and I released a trivially exploitable kernel 0-day. It was actually fixed if you were running with administrator privileges or if you were running your process as system. But it was not fixed if you were running your process as a normal low-privilege user. Luckily, Microsoft was able to come up with an out-of-band patch in super fast time frame, so they released an out-of-band patch for the memory manager in the kernel just 2 days after I published my initial blog post. So really thank you for that. I'm going to do a demo how I came across to find it, and we'll find it by looking at the memory map we had just had a look at. And there we'll see that the PML4 self-referential entry, which is the base of the page table, it's mapped straight into user mode. So let's switch back here. The copying is still going on. It can do that. But here I do have a vulnerable virtual machine that is vulnerable to the, it's patched with the January patches from last year, so it's vulnerable to the Total Meltdown vulnerability. So let's mount the memory process file system, and this is how I came across it. Of course, I'm cheating a little bit here today since I'm using the actual vulnerability to mount the file system. When I was initially researching this, I was using the FPGA hardware we just showed. You can click into the file system and go into some process, for example, the CMD, and let's have a look at this memory map. Open it in our favorite text editor. And it looks pretty normal here. It looks how it should do. And we have some memory addresses and some modules. This is all normal until we scroll down at the end. And what is this? This is memory addresses that are starting with lots of Fs. And they are not marked as kernel pages. So what is going on here? Addresses starting with lots of Fs, they are supposed to be, or they are normally belonging to the kernel itself. So this is really strange. I was also able to dump physical memory from this system at quite high speeds, around 2 gigabytes per second, and I was also able to gain kernel code execution. And here I have kernel code execution. I loaded my backdoor module at this physical address. So what is going on here? Let's have a look at it. Let's have a closer look at it. Going into the CMD process. And let's have a look at the PML4s, or the bases of the page tables. Since the Meltdown patches in January last year, we do have 2 different page tables. That's the actual Meltdown fix. We have the original PML4, which is nowadays is reserved for admin processes and kernel view of processes. And then we have the user mode PML4. That is a separate one, the new one. Let's have a look at the first one. Let's do a hex dump of it. And this is the original PML4. And in Windows 7, we have a really special PML4 entry in the page table, topmost page table, at offset F68. It's now randomized in Windows 10, I believe, but in Windows 7, it's still located at offset F68. And it basically references the PML4 itself. And this is in little endian, so it actually ends with 67. And 7, if we read the Intel manual, it means that it's active, it's writable, and it's accessible from user mode. And that shouldn't be. If we have a look at the user mode PML4 as well, we see the same thing. At offset F68, it ends with 67 or ends with a 7, and that is the actual vulnerability. the actual vulnerability was one single bit set in error. And this allowed any user mode process to access its own page tables. And if you could access your own page tables, you could do like a very trivial exploit. I don't even want to call it that because it was so simple. You could insert your own fake page table entries and basically do read-write to the entire physical memory. And in that way, you can take pretty much total control of everything. So I didn't even need to do any API calls for it, just insert a page table entry already mapped in process memory and read arbitrary physical memory. Another use case that I didn't expect at all myself, it was something I became aware of last summer. It was cheating in games. It turned out that I didn't know this, but anti-cheats, they are quite powerful pieces of software. They detect most software-based cheats, if not all. And in theory, a hardware cheat, it should only be seen as a PCI Express device on your gaming system. And then you could do DMA from this PCI Express device and ship the memory to another computer and do the memory analysis in there, and the anti-cheat cannot reach into that separate computer. And you kind of need to have PCI Express devices in your gaming system, right? Graphics cards and things like that. You could do things like a read-only thing. You could do like a map decloak and spy on your opponent's locations in the game's process, for example, if they are in there, and they are quite often in there since for performance reasons. You could also do read-write, but writing might be a little bit more easily detectable. I first became aware of this last summer, where there was like a big cheating scandal in the CSGO community. It turned out that people had been cheating at home and on LANs to which it was okay to bring your own computer, so you could have this FPGA board inserted into it. And then a couple of months later on, even a cheat-focused fork on my PCILeech software appeared on GitHub. And this is how it looks like. If you look very closely, this is the PCI Express Screamer FPGA board inserted in this gaming PC. And if initially anti-cheats didn't detect this at all, so it was like touted as the next generation of cheating, the completely undetectable cheating and the future of cheating. And that was quite not the case. For example, it took a while, but eventually the anti-cheats caught up. ICEA, which has a quite good anti-cheat, when they started detecting it, they wrote a blog entry about it, geared toward the gaming community, when they explain on a very high level how it looks like that you have a DMA device in your gaming PC, you read the memory to your attack PC, and you somehow ship the location on your opponents to a phone, for example. They claimed that cheats had been selling in the range $1,500 to $5,000. And of course, when they initially started doing detection, it resulted in a ban wave of both cheat customers and developers. Initially, it was quite easy to detect, since most people were actually using my default bit streams for the FPGA, which has some hard-coded device IDs in there. So just look for those device IDs, and right, you're probably a cheater. But they also claimed that they're able to detect hardware-based cheats, even when disguising the cheat as a legitimate device. I'm not 100% sure that's true in all cases, but it certainly makes hardware-based cheating a lot harder. So when I was creating the memory process file system, I had some overall design goals. The most important one was to have it really easy to use, something that I could use myself. I'm kind of new into security myself, and I don't know my way around all these command line tools, so it would be nice to have something I could just click on file and get it to work. But I needed something that was quite powerful as well. I wanted to do this design as modular as possible. It should be able to, users should be able to extend upon it by themselves without having to recompile the whole thing. Since people were already including my stuff in their own projects, and it was coded in C, a C API was given from the start, And I also thought Python is super popular within the security community and also within the memory forensics community, so let's add Python support as well. And then, since I'm doing it as a file system, when you're clicking around in this file system, clicking in a folder, I'm doing on-the-fly memory analysis, you can't afford to wait 1 or 2 minutes for some analysis to take place and then show the result. So it needs to be really high performant. This is how it looks like. I use a third-party, really awesome file system driver, which is called Dokan. It takes care of the hard parts, like having a kernel driver for the file system. All I need to do is to implement some really simple callbacks in my memory process file system executable, which is pretty much a very thin wrapper which forwards calls like list directory, read file, and write file to the main analysis library. And in here, every memory analysis steps are taking place, and I do the virtual to physical memory translations, for example, and I do support communication with external plugins, either coded as native DLLs or Python files. If you're doing a Python plugin, you may want to call back into the main analysis library by using the Python API, or if you are including it in your own projects. And also, in order to make it even more modular, I decided to break out the physical memory acquisition functionality to a separate library, which I call the LeechCore Library, which is something I'm releasing here today. It is a small library that focuses totally on physical memory read and write. And this separates memory acquisition from analysis in a really nice way, and it would also allow me to reuse this component across my projects. I do support the initial USB 3380 hardware, but also the FPGA hardware. New for today is also that I have some really awesome integration with MatSwish Dumpit tool, which allows us to capture live memory from a running live system and do on-the-fly memory analysis. I also do support the recall Win PMEM driver. We can also open memory dump files, various types of memory dump files, raw linear memory dump files, full crash dump files, and even Hyper-V save files. More recently, Synactive also contributed a quite interesting patch for HPILO. It turns out that if you do have a compromised HPILO, the BMC, you can insert a backdoor into that one that would allow you to do DMA straight into the host operating system of that server. And then you can use my tools to do that as well. And then something new for today as well is that I'm releasing the Leech service. It's a capability that allows us to basically connect to a remote system using this software, and the remote connection is secured by Kerberos mutually authenticated RPC. And once we are connected to the remote system, we can use any of the above memory acquisition methods I discussed just now. The main analysis library looks something like this. I have the API on top, which the memory process file system executable is calling into, or other programs may call into it as well. And then I do the physical memory acquisition in the separate library. And on the very bottom in the analysis library, I have a really simple object manager, which would allow me to do things like object reference counting, which allows me in a really nice way to implement some caches. For example, I do cache the physical memory and the page table separate. And then we need to have a layer that takes care of the virtual to physical memory translations. And in order to do so, we need awareness of which memory model the target system is using. For example, if I'm using the 64-bit memory model, physical address extension, or the standard x86 32-bit memory model. And then, of course, we do lots of analysis things in here as well. I do also have the concept of a process object, which contains a memory map object and a module map object. We do have an object manager in there, a plugin manager in there, which allows me to communicate with the external plugins, either coded in small Python files that you just drop into the directories, or native DLLs coded in C, for example. And if you're running against live physical memory, or if you're acquiring memory with dump it in its live KD mode, for example, a memory that may change, we do have a small housekeeper thread in there as well that keeps track of things like background process refreshes. And if we connect everything together here, we might have some incident response scenario. For example, we may have a suspicious process on a computer that is quarantined to a separate VLAN, but we might have limited bandwidth to that computer, and we might even have some latency over the network. And a full memory dump of a big system with a lot of RAM in it, it's just horribly slow to do that over the network. The solution, it might be to retrieve only the memory you actually need to do your analysis and analyze it with the memory process file system. So let's do another demo. Let's analyze some live malware memory on a remote system. And we are going to do that by clicking on Files. So here I do have a remote system, or it's a virtual machine here on my demo computer, but it's remote for this purpose. We are starting, we see this IP address here, and we are starting the Leech service with dump it in its live KD mode, which just allows us to capture live memory from this system. We're starting it in interactive mode, since I don't want to run it as a service here, and also in insecure mode, which disables the Kerberos authentication steps, since this computer is not part of a domain in this demo computer. And now it should be ready to connect to it. So let's do that. So here I'm connecting to it, to a remote system, using RPC in the insecure connection and the IP address, and we are going to use the dump it device to acquire memory. So we have it started here. So let's try to click into it. You can click into the names folder, for example. It's yeah. And if we check all the processes in the names folder, we have a really strange process looking at the end here. It's an old Citadel malware sample I found. It's nothing fancy, but we can have a look at its memory map, for example. And remember, the memory map is acquired live by walking the actual page tables that the CPU uses to execute code and read data, so there's no really way around this memory map. If you need to execute code, you need to be in here. And if you scroll down, we see some suspicious section here. Usually a PE section should be read execute in one page the first, and this is a really big read write execute section, so it looks really strange. We can have a look at the virtual memory of this remote process as well. And in there we can, for example, we can search for some values. And yeah, this Trojan has some blacklist for the antiviruses in here, so I knew what to search for example. And if we are running with a write-capable device, we can write back after we make changes here as well. But we are not doing that right now. So there are really big advantages with physical memory analysis. You may already be using tools as volatility or recall. This is not a replacement for those tools. It's more like a complement in some scenarios. It's quite okay performance even over a little bit laggy networks, as long as the latency is not too high. And the focus for me in the near future is to add even more core performance optimizations which would allow me to parallelize remote reads even more in order to reduce latency impacts. And also having a multi-threaded design is super awesome, since it allows me to do things like background process refreshes and background refreshes, so the user never notices those things. The analysis capability is a little bit limited at the moment, but I do plan to add more analysis plugins in the future. Let's have a look at the Python API as well. Let's analyze some live memory in the Python as well from this remote system by using the API. And let's code a small program in Python that locates all read, write, execute sections in all processes on the remote system. So we are using the same remote system, and let's open Python. First, we need to import the analysis library. And once it's imported, we can have a look at the different functions in it. We have quite a few of them in there. And first, we need to initialize the actual library with a connection to the system that we wish to acquire memory from, the remote system in this case. And we are going to use dump it once again to acquire that memory. Once we initialize the connection, we can retrieve the PID of a given process in the remote system, for example, the cmd.exe, and we are going to print it on the screen as well. And this is the PID of the cmd on the remote system. We can retrieve some process information on the remote system. We retrieve it as a dictionary containing information for all processes, and we are locating it by using the PID. And if we check the process information for the CMD, we see information like the physical address of the PML4, the directory table base. We see its name and the eProcess virtual address of the eProcess structure in the kernel, for example, and also the virtual address of the PEB. And we can have a look at the whole dictionary, of course, but that's a huge amount of data that's not really suitable to show in a screen like this. We can list all processes in the remote system again. Let's do the same call and get the process information for all processes, but let's iterate over it. And for each process, let's print its PID and its name on the screen. And this is the complete process listing of the processes in the remote system. We can retrieve the memory map for a given process, the CMD again for this example, and let's have a look at entry number 300 in this memory map, for example. Here we see the virtual address, the base of the memory map entry in the virtual address. We see its sizes. It seems like it's 3 pages long in this case. It seems to be belonging to the NTDLL, and it seems to be like a read-execute piece of memory. Once we have all this information, it's all that we do have to code our small demo here. So let's do that. Let's retrieve the process information for all processes, and let's iterate over it. And for each process, let's retrieve its memory map. For each entry in the memory map, we are going to have a look if it's a read, write, execute entry. If it is, we are going to print it on the screen, together with its, the PID and the name of the process. And in order to make it a little bit more readable, we are only going to print 2 entries per process. And now, as we go, we are actually making an RPC connection to a remote system and using dumpit to acquire live memory from the remote system and return it to my presenting computer here, in which all the analysis steps take place. And this is done live, and as you can see, it's quite fast. We are already done. We have some read, write, execute sections in the kernel, for example. It seems like we have it in the OneDrive, the Spotify, our Trojan, and also in PowerShell. It seems like we do have one of those. We can also read and write to physical memory. We can read and to virtual memory as well. The first argument is the PID of the process that we wish to read virtual memory from, or if we're using -1, that means that we're going to read physical memory instead of virtual memory. We are reading from address 1000 in hex and reading 256 first bytes and printing it in a nice way on the screen. And this is live memory from this remote system. The Python API, it looks something like this. In addition to read and write functionality, we have read-write functionality. We have the different functions related to listing process information. For example, retrieve the list of PIDs, retrieve some process information, retrieve process memory maps and module maps. And for modules inside the processes, we can list its exported functions, imported functions, data directories, and PE sections. And also, even though the memory process file system isn't mounted, it still exists in the main analysis library in a virtual way, sort of. So you can actually list its directories, read those files, and write to those files. When I was creating this, I had a big focus on performance, and I'm really happy to have been able to complete multi-threading just before BlueHat. It makes a huge difference. And also in memory caching and intelligent parsing. And the goal is to avoid scanning large chunks of memory for signatures as much as possible. One example of this is how I locate the kernel directory table base in the kernel base when I'm starting this. The directory table base, or the PML4, as you all know, it's required to translate virtual addresses to physical addresses. And we need to get a hold of that one at the very beginning. It might already be known to the underlying device. For example, if you are opening a crash dump file, that information is already inside the crash dump file. Or if you are acquiring memory with either dumpit or pmem, we can just query those ones for this value, and then we're all done. But if we are using the FPGA or a raw linear memory dump, for example, we don't have that luxury, so we can look for something called the low stub. Initially, a couple of years ago, I didn't know what this was. I only know it was super useful for my purposes. And it was a memory structure that was usually, not always, but usually located at offset 1000 in physical memory in hex. And I didn't know what it was, not until Alex Ionescu did a really nice talk at Recon Brussels 2 years ago, when he explained that this is the low stub. This is a memory structure that is there for bringing the CPU back up when it unsleeps the computer, recovers from sleep. Its CPU starts in 16-bit mode, so it needs to go into 32-bit mode, and then 64-bit mode in order to restart the kernel again. And this is where this memory structure comes in place. At offset A0, we have the PML4 of the kernel. And at offset 70, we do have an entry into the entity kernel. It's not the base of the kernel, but it's kind of fine because it's not too many pages to scan back a few pages, so it's not really impacting performance. And as a last resort, yeah, if we don't find it, we might have to do some scanning as well. So let's do another demo. Let's do a physical demo this time as well. Let's try to write to some memory as well. Let's hunt for some data in the process heap, and let's overwrite it on a separate physical system. So here I have, if we can have that one on the, so yeah. I'm starting Notepad on this system with some text here. And let's see if we can find that text by editing some files. I already have the mounted here with FPGA since before the actual file system. So let's have a look at it. Let's click into the Notepad process. It already appeared here since I started it just a while ago. And here we can we have the memory map, and for each memory map entry, we are also creating a file in the memory map directory. So let's edit some files here. Let's do it in Ubuntu this time. I need to mount the actual drive first. And let's go into that directory. Before we start, we need to search for some text. Let's search for the hello text. And if we check that, what is in hex ASCII, it's this value. And in this directory, it contains file for each memory map entry. And the text in Notepad, it should probably be stored on the heap somewhere. So let's, and it should probably be stored on the primary heap, heap 00 in my program. So let's have a look if we find some. We need to go into that directory as well, of course. And better luck now. And let's open some. We have a couple of heap entries here, and let's open one of them in our hex editor, one of the larger one, and try to search for this text, the text hello. And in Notepad, everything is in UTF-16, so we need to zero pad every second byte. And here I do have some text that looks, it looks promising at least. So let's try to change that and see what happens. And hit save. And nothing changed until I just click somewhere on this system, I hope. No, this is not how it's supposed to be working. Let's try to. Let's try again. Why is it not? One failed demo out of the last one, so it's. I think we don't. Maybe the text is stored in multiple places or another part of the heap as well, so it might be more places. We can have a quick look if we find some more texts in here. Probably not. Yeah. But anyway, one failed demo out of quite a few ones. It's kind of okay, I hope. Anyway, the memory process file system, it's a work in progress, and a lot of future work remains. It's a hobby project of mine, so I do have limited time. But I want to add page hashing really soon. I want to be able to do things like signature mashing, and also it would allow me to do things like remote background low bandwidth cache coherency updates to make it more user-friendly, and also it would allow me to capture remote memory at lower bandwidths as well. I wish to add more functionality and features, such as additional analysis capabilities, and also support for non-Windows operating systems as well, but that's a huge work item. And of course, additional memory acquisition methods. And to sum everything up, the memory process file system, it's a multi-threaded library, which is a really easy point-and-click file system-based memory analysis tool with a strong Windows focus. It has an API for Python, C, and C++. It comes with a wide range of memory acquisition methods, both hardware-based methods and software-based ones. And it's completely open source. It's available on my GitHub, and please do have a look at it. Thank you.